Let's see how to solve this IBAA higher level question involving integration and the method of substitution, in which we're told, using the substitution u, which equals to sine of x, find the integral that we can see here. Now if you're up for it, go ahead and press pause and try solving this before watching the rest of the video. Either way though, I'll get started. Okay, now as I often do, I'll go ahead and write SOL for solution. And here, since we're told that we have to use the substitution u equals to sine of x, I'll quickly make a copy of that, so u equals to sine of x. And a very important thing to do here is to make note of the derivative, so du dx, which I'm sure you're comfortable in seeing, is equal to cosine of x. And the reason why it's so important to make a note of du dx here is because an important part of the process of the method of substitution, in which we're effectively changing the variable of our integral, is to make sure that the derivative, cosine of x, appears in the expression we're trying to integrate. And hopefully you can appreciate that since du dx equals to cosine of x, and since we have a cosine cubed on our numerator here, that shouldn't be too difficult. And so let's see how to do that. I'll quickly make a copy of the integral, so we have the integral of cosine cubed of x over the square root of sine of x. And as I just said, I want to make sure that the derivative du dx appears clearly, or I could also say is separated from the rest of the expression in this integral. And here's how I'll do that. I'll go ahead and say that this is equal to the integral of cosine squared of x over the square root of sine of x times cosine of x, and we have our dx at the end here. Now, making sure that the expression for the derivative du dx appears separately in this expression is very important, as combining our expression for du dx with the dx we see here is exactly what will allow us to change our differential dx to the differential du. And we'll see exactly how that works in just a minute. The method of substitution is often called change of variable. The reason being, our goal here is to rewrite this entire integral in terms of the variable u. And as we just said, the combination of cosine of x and dx is what will allow us to write du instead of dx, so that's taken care of. And since u is equal to sine of x, we'll need to make sure that this cosine squared of x is written in terms of sine of x. And for that we can make use of the well-known result, sine squared of x plus cosine squared of x equals to 1, to rearrange this to make cosine squared of x the subject. Indeed, using that, we can quickly state that cosine squared of x is equal to 1 minus sine squared of x. And so replacing the cosine squared of x we have here by 1 minus sine squared of x, this integral becomes the integral of 1 minus sine squared of x over the square root of sine of x times cosine of x dx. And at this stage, we're ready to change the variable and rewrite our integral in terms of u. Indeed, looking at all of this, we now know that the cosine of x we have here, well, that can be replaced by du dx. And since u is equal to sine of x, the sine squared of x that we have at the top here, well, that will just be u squared. And the square root of sine that we have on the denominator, well, that's just going to be equal to the square root of u. In other words, this integral can now be rewritten as the integral of 1 minus u squared over the square root of u times du dx times dx. And looking at the du dx times dx we have at the end here, the dx's we have here cancel each other out, and we can write our integral as, well, let's see, that's equal to the integral of 1 minus u squared over the square root of u times du. And let me stop there for a second to highlight the fact that the last step we've just seen, in which the dx's cancelled each other out to leave us with du, showcases the importance of making sure that the expression we have for du dx appears clearly, or even separately, from the expression we're trying to integrate. That being said, I carry on. At this stage, we've completely rewritten our integral in terms of the variable u. Indeed, there is no x left to be seen. And to integrate this, well, we can use the power rule for integration. Indeed, if I split that into two separate terms, so I'll say that's the integral of 1 over the square root of u minus u squared over the square root of u with the du at the end here, then I can rewrite each of these two terms as a simple power of u. And that would be equal to the integral of u to the power of negative 1/2 minus u to the power of 3 over 2. And at this stage, I apply the power rule so that we have 1 over negative 1/2 plus 1 times u to the power of negative 1/2 plus 1 minus 1 over 3 over 2 plus 1 times u to the power of 3 over 2 plus 1. And of course, I'll have a constant of integration at the end here. Now, negative 1/2 plus 1, well, that's just equal to 1/2, so we have 1 over 1/2 times u raised to the power of negative 1/2 plus 1, which again is 1/2. And we take away from that the second term, for which we have 1 over 3/2 plus 1, and 3/2 plus 1, well, that's 5/2, or 5 over 2, so this becomes 1 over 5 over 2, times u raised to the power of 3/2 plus 1 again, so that's 5 over 2 again. And again, we have our constant of integration c. We're nearly there. This 1 over 1/2 turns into 2, and this 1 over 5 over 2 turns into 2/5. So this becomes 2 times u raised to the power of 1/2 minus 2/5 of u raised to the power of 5 over 2 plus c. And using the fact that the power of 1/2 is the square root, we could also write this as 2 times the square root of u minus 2 over 5 times the square root of u to the power of 5 plus c. And now to state our final answer in terms of x, all we have to do now is replace every u that we see by sine of x. And so that would be 2 times the square root of sine of x minus 2 over 5 times the square root of sine of x raised to the power of 5. So I'll write my power of 5 here, plus the constant of integration c. And that's the final answer. And there we go. That's how we can solve this IBAA higher level question on integration using the method of substitution.